Yeah. Can you see the screen now?
Yes, sir. It is visible. It is visible.
Okay, fine. Shall I start now?
Just a minute, sir. Give me just 1 minute.
Yeah.
So, good morning and welcome to all the participants in this second session of day 3 in this STTP. This particular session speaker is Dr. Prakash Kulkarni. He is Chief Scientist as well as Professor in IISc Bangalore. Sir has obtained both Master's and Doctoral degree from Department of Aerospace Engineering, IISc in 1982 and 1986 respectively. He has carried out his postdoctoral research in the area of computational fluid dynamics both in India and abroad for a period of 3 years. Joined as a faculty in the Department of Aerospace Engineering in 1990. Sir is having wide experience in both algorithm development and applications of CFD, computation of complex flows over complex geometry, solved several challenging problems of interest to aerospace industries. Sir is having research and teaching experience of more than 25 to 30 years. He spent 2 years during 2002 to 2004 at Tohoku University, Sendai in Japan, in Shockwave Research Laboratory and Biomedical Laboratory for Mechanical Engineering Department. He has received many awards, awarded with National Award for Aeronautical Society of India for the contribution to the aeronautics. He has published more than 150 research papers in various journals, conferences and symposium, guided several MS and PhD theses in the Indian Institute of Science. Currently is Professor and Chief Research Scientist at IISc Bangalore. So thank you very much, sir. We are very lucky to have you in this particular session. You can start your session now, sir. Thank you.
Yeah, thank you very much, Thakurji. And first of all, I'm sorry, there was some problem with network and then laptop. Sometimes these things happen when you don't want it to happen.
No issue, sir. No issue.
Yeah, okay. So I would like to share some of my experiences and would like to present before you some of our activities. And the topic is today CFD. There is a computational fluid dynamics, which we consider it as a revolutionary tool in engineering design and analysis studies. Already Professor Tucker has introduced me. I will proceed to the next slide. I would like to express my gratitude to the armed forces in the country who are protecting us relentlessly. I have deep respect for our defense sector. And I thank the organizers of short-term training program on applied CFD for automotive, space and defense sector for their kind invitation for delivering this lecture. And I'm also thankful to Dr. Vishal Singh and Dr. Maharishi Thakkar for their coordination. And thankful to all my colleagues, students, project engineers from IISc and from various academic institutes and research laboratories from various parts of the country, and some of them could be even in abroad, for their kind cooperation and contribution to this presentation. Today, incidentally, March 3rd is Founders Day in Indian Institute of Science. It is the birthday of J.N. Tata, who is the founder of our Indian Institute of Science. And locally, this institute is more known as a Tata Institute rather than Indian Institute of Science. This institute has completed more than 110 years now. I think it must be 115 years now. And Tata was responsible for establishing this great institute, which offers varieties of opportunities for conducting research in both science and engineering. So I want to express my gratitude and also a big tribute to Sri J.N. Tata, who is responsible for this great institute. The outline of my talk would be something like this. I would like to give a brief introduction to CFD, and then algorithms, which play a very important role in numerical simulations. I would like to talk about few algorithms, and then very briefly I will talk about growth of computing power and applications in CFD. Computing power is very important in the area of numerical simulations, without which we cannot do much work in this area. And also I will show you CFD map of India, where all the activities of numerical simulations of fluid dynamics is taking place, and multi-institutional tasks and fruitful institute industry interactions, which we have been having for the last 30 to 40 years. And I would like to present before you some promotional activities, how we would want to promote this numerical simulations in fluid dynamics. Various activities have been identified. I would like to share some of my experiences with you. And finally, I would like to draw some conclusions before I end my talk. First of all, let us understand what is this CFD. We deal with fluid dynamics, and so many physical processes, they keep taking place around us, where fluid dynamics is the key issue. And fluid dynamics is the key to our understanding of some of the most important physical process or phenomena. They are taking place in our physical world. They could be oceanic currents, weather systems, like aerospace vehicles, subsonic vehicles, transport vehicles, supersonic jets, and hypersonic vehicles like various missiles. And also it could be a civil engineering problem like flow over tall structures, buildings, and also it can be a biofluids, flow through the artery, blood flow analysis, and it could be heat and mass transfer in vessels, and so on. First of all, let us understand what is this physical process and how we want to get information or get knowledge or get to know about it. For example, any physical process you take, weather changes, flow over an aeroplane, and as I mentioned, winds across the tall structure, or it could be volcanic eruptions. All these physical process, we can understand it by either experimental studies or theoretical studies. Sometimes you require both, because you require theoretical understanding to conduct careful experiments or conducting experiments carefully. So there are no independent tools. I consider them as they go hand in hand. The process involving the behavior of fluid flow in different conditions, it can be approximated by a set of partial differential equations, which we call them as PDEs, and they lead this approximated PDEs, they form mathematical model. And obtaining solution to this mathematical model, either analytically or numerically, it forms a very important branch of science. Obtaining the solution for this PDEs by numerical procedure or by discretization is called computational fluid dynamics. And it is very essential to understand what is CFD and why we need CFD techniques. That means, to summarize, either we can study the physical process by conducting various experiments, or by understanding this physical process by making varieties of mathematical models, the partial differential equations, which represent this physical process. So the physical process could be understood either by theoretical studies or experimental studies. And in theoretical studies, we can form the mathematical model, and the mathematical model can be solved by analytical methods, which give you the exact solutions. Sometimes obtaining analytical solutions for these PDEs is not possible because they are highly nonlinear, coupled, and complex. So in such cases, we require numerical methods, and the area of science is called computational fluid dynamics. We approximate rather we say that we obtain approximate solutions to the partial differential equations. Whatever we obtain from CFD is not exact solutions, they are approximate solutions. That is why we need to verify, validate, and certify the solutions obtained by the numerical simulations. Next, I would like to give a very brief historical sketch. Around 17th century, the birth of experimental fluid dynamics took place mainly in Europe, and gradually the development of theoretical fluid dynamics started in Europe around 18th and 19th century. And it will be, you will be surprised to know that first experimental research started in fluid dynamics before theoretical fluid dynamics. And then around 20th century, the practice of fluid dynamics involved pure theory on one hand and pure experiments on the other hand. Because of the communication gap, it was not possible for various scientists to interact with each other. Around 1960, only two approaches ruled the field of fluid dynamics. We did not have anything, like what we talk CFD today. So up to 1960, one can say that fluid dynamics was understood either by pure theory or by conducting pure experiments. So the physical process, the type 1 analytical solutions in closed form, we can obtain exact solutions, or we can model them by PDEs which are highly nonlinear, complex, and coupled, and analytical solutions do not exist. So we solve such equations by approximating. That means we discretize the entire space and then try to solve these equations. Therefore, we obtain approximate solutions for these partial differential equations. So birth of CFD, I would like to say, with the advent of digital computers around 1960 to 70, because without computing power, you cannot do any numerical analysis. So the availability of digital computers helped the growth of computational fluid dynamics. So with the advent of computers combined with development of accurate numerical algorithms for solving physical problems, it revolutionized the study of fluid dynamics. That is how the growth of CFD took place. That is why we most often call it as a revolutionary tool in understanding engineering and problems in science. So introduction of a new approach called computational fluid dynamics. It is the beginning of CFD era, a third approach we call. We can see here, it is the pure theory was there before, and pure experiments were there, which were independently studied. And then around 1970, 60 to 70, roughly you can say around 50 to 55, 60 years back, a new approach, a third dimension called computational fluid dynamics took birth. And in this computational fluid dynamics approach, we solve the partial differential equations which govern the physical process of interest by numerical methods. So CFD added third dimension to the existing two dimensions of studies of fluid dynamics, that is pure theory and pure experiments. So what is CFD? CFD involves three letters, that is C and FD. C stands for computational and FD stands for fluid dynamics. What is this computational? It is not just computer, it is not just a software which runs on the computer, but computational involves a list of topics like development of algorithms, and to develop such algorithms you require various numerical methods, and there are certain issues related to computers. They could be parallel computing. In parallel computing, the issues like hardware, software, how to communicate between two different nodes, such very fine aspects of computer science comes into picture. You know, operating system, application software, and all these issues are, you know, they are in computational aspects of CFD. And fluid dynamics, of course, deals with physical process, basics of fluid dynamics, and what are the governing equations and various levels of approximations. What are these levels of approximations? A physical process can be either inviscid flow or viscous flow with the turbulence. So it depends upon the physical process what you want to understand. Different levels of approximations could be made in your basic governing equations. So the modeling, the model what you consider, it becomes very important. It should be properly approximated. So with this, you should have one geometry configuration, that is over which you want to solve these fluid dynamical equations, and boundary conditions, because boundary conditions are the one which drive your numerical solutions to the correct solution, I can say, or I can say it will drive numerical solutions to the accurate solutions. So this computational and fluid dynamics and this geometrical configuration over which you want to solve your equations and boundary conditions, all these things become very, very important when you consider any physical problem by CFD analysis. So CFD, what you require, governing equations of fluid dynamics, you require mesh or grid on which partial differential equations are discretized, and state update formula, that is state update for partial differential equations plus boundary condition to advance the solution at a grid point. A computer code you require, either written in Fortran, C, C++, or MATLAB, or presently you have lots of software tools. You require a computer code and post-processing of massive data. This CFD generates very huge data. You cannot read the numerical numbers and understand the physical process. You require a post-processing data, which I will talk about it in my further slides. So if CFD involves all these things, and CFD codes are very useful in engineering design and analysis studies. So in a nutshell, you have partial differential equations like Euler equations or Navier-Stokes equations, or even just a Laplace equation. All these equations depending upon the kind of physical process you are considering. So this PDE with the boundary condition, it forms the mathematical model, and then you have the space discretization. Suppose you have an aerofoil. I want to study the flow around the aerofoil. I would like to discretize the space around the aerofoil, and I call them as grid points. It is called numerical discretization. So at every grid point, you solve the partial differential equation, and you get the several coupled ODEs, and then either by time marching or by space marching, you start evolving the solution. At every grid point, your numerical solution is updated. The boundary conditions on the body and the far stream, I will talk about it, they make a very important aspect, or they are very important in understanding the CFD simulations. So with this time marching, you have a state update. So you are updating the solution at every grid point. We call some of the points as the interior point state update and boundary point state update. Boundary points where the boundary conditions are implemented. They with the numerical solutions, boundary conditions are held constant unless it is a moving grid points. Yeah. So if you want to understand CFD, you have to do at least for the beginner, there could be an introductory CFD level, and for the experienced person, there could be a introductory CFD level 2, level 1 and level 2. So that is how the CFD is taught in some of the institutes. So in CFD level 1, I consider understanding physics of the fluid flow, governing equations, boundary conditions. What are the different partial differential equations we come across which are useful in the studies of CFD, and the basic of numerical methods and stability, convergence, accuracy, consistency, and what is mesh and what is grid generation, and basic CFD techniques for test cases. All these things form a basic level. I call it as the level number 1. And in level 2, you repeat some of these things with more deep understanding: physics of the fluid flow, governing equations of fluid dynamics, advanced CFD techniques like upwind methods, application of CFD techniques to heat equation, ADI methods, Laplace equation, upwind methods, compressible Navier-Stokes equations, turbulence, parallel computing. That is how you keep on adding more and more complexity to the physical problem. That is, whatever physical process you want to understand, you make it more and more complex, and you need more and more advanced technology, advanced numerical methods, and also at the same time, you require more powerful computing power, computers. So you require a flow solver which solves the partial differential equations. You require geometry of configuration. You require mesh generator because you have to discretize the space around. And finally, you require a post-processing and then analyzing the data to get or to retrieve information from the huge data. Yeah. So whatever I have said till now, I want to represent it in a pictorial form. So here, if you consider this green, it is a very simple configuration. I call it simple configurations of approximated governing equations. Okay, you require simple algorithm and simple computers. For example, you want to solve just two-dimensional problem like aerofoil. I want to understand flow over an aerofoil. It can be subsonic or it can be even supersonic. How the shock formation take place. I want to capture the shock in 2 dimension itself. You can do a lot of numerical experiments. They are very simple, and you don't need any advanced technology. The existing technology you can use. You can model the equations in 2 dimensions, and you can use simple computers. Even on laptop, you can solve such problems. And then this light color, pink, it is complex configurations with the simple physics. I don't want to consider viscous, turbulence. I don't want to add more complexity into physics, but a geometrical configuration can be complex. You want to solve just inviscid flow over a missile type of configuration, or a transport vehicle, or it can be even fighter aircraft. So a geometry can be simple, as a complex, and physics could be simple. So sophisticated methods and relatively, bigger computers could be used in such cases. So next level is a more complex one. Complex configurations like three-dimensional bodies. We come across varieties of configurations. Recently, you have seen Rafale, and recently there was an air show in Bangalore. You must have seen the varieties of aircrafts flying in the sky, and they do a lot of maneuvering. Maneuverability is one of the most important aspects we look into in defense-related aircrafts, whereas in transport vehicles, we look for stability. I want to safely reach from point A to point B. So transport vehicles will have more stability and less maneuverability, whereas fighter aircrafts, they will have a large maneuverability controls, and at the cost of stability. So that is how this third layer, it is a highly complex geometry and highly complex physics. You require advanced algorithms and high-end parallel computers. In fact, in very big R&D laboratories, maybe it can be in VSS Trivandrum, ISRO, Indian Space Research Organization, or BRC Mumbai, or it could be in NASA, National Aerospace Administration, and so many other places in Europe, China, and all over the world. They use very massive computing platforms that are called parallel computing platforms. So this in 3 dimensions, one is fluid dynamics, governing equations, and the other one is complexity of geometry of physical body. It can be a very complex geometry, like you must have seen several fighter aircrafts, or even some missiles. It's wing body junctions, tail configuration, and nose wing. I know all this, they form some kind of complex geometry. They offer a lot of challenges for the generation of mesh around the body. So I classify them as complexity of geometry. And then one more dimension is algorithms and computers. More and more complex geometry and more complex physics, you require more advanced tools and more advanced numerical algorithms. Yeah, CFD, which has grown to a very mature stage now, it will continue to play a very important role in the analysis and design and product phase. And CFD always complements the other 2 approaches, that is experimental fluid dynamics and theoretical fluid dynamics, but it will never replace either of them. Sometimes when you get very good results by using CFD techniques or CFD tools, you will be convinced that I don't require any more experiments, or I don't require any theoretical studies to be conducted anymore. It is not true. Numerical simulations, accurate numerical simulation will help in conducting experiments more meaningfully, more carefully, so that the experimental data, what you obtain, becomes a kind of standard platform where validation could be conducted. I will come to that. Verification and validation, they become very important aspect of numerical simulations. So I would like to say CFD will never replace either experimental studies or theoretical fluid dynamics, but it will complement, it will help in understanding the phenomena in much better way. So need of the hour is to evolve a proper balance among all the three approaches: experimental, theoretical, and numerical. So CFD helps to interpret and understand the results of theory and experiments and numerical experiments, and that is why we call it as numerical wind tunnel. You can carry one hands. You must be aware of several industrial packages commercially available for CFD simulations, like ANSYS, MSc software, CFD++. There are several for both pre-processing and post-processing. We call them as numerical wind tunnel. That means you can carry it. You can carry in your laptop and you can conduct several experiments. So it is a mobile wind tunnel, something like that. So it is a CFD map of India. I would like to share with you some of my knowledge. So there are several IITs and many regional laboratories and research laboratories, and maybe some of them I may be here who have started activities recently, where CFD is being pursued. For example, IIT initially it started with IISc, and then various IITs, IIT Kanpur, IIT Mumbai, in Mumbai IIT, BRC. In Bangalore, we have IISc, NAL, and various DRDO laboratories like GTRE, ADA, ADE, CAPS, and so on. IIT Chennai, DRDL Hyderabad, who are now in fact pioneers. They have several in-house developed codes, and initially, I will come to that, around 30 to 35 years back, we started activities. We in fact helped them in establishing CFD group in Hyderabad. Now, they are, I can say that one of the best groups in the country. IIT Kharagpur, IIT Kanpur, and UPS Dehradun, IIT Guwahati, and so on. And there are so many other institutes which I may be missing in this map, but there are so many other places also where CFD activities are rigorously pursued. And I would like to summarize whatever I have been saying in few slides now. That is, we have basically flow solvers and we have mesh. And flow solvers, meaning we discretize the space and solve the partial differential equations by using numerical methods. These numerical methods could be central differencing, or it could be upwind schemes, or it could be grid-free algorithms. We also call them as meshless methods. So there is no need to generate a mesh. Any randomly or arbitrarily distributed points around the physical space. Suppose you have an aerofoil, you can randomly distribute the number of grids or grid points, or we can call it as cells, over which you can solve the partial differential equations, and there is no need for any special grid generation. If you want to generate the mesh, there could be structured grids, unstructured grids, hybrid grids, which combines both structured and unstructured grids, or it can be randomly distributed grid points. So this generation of mesh forms a very important aspect of CFD, because good quality mesh is responsible for obtaining accurate solutions. There is a saying, a mesh, either it can make or break the solution. A bad mesh will totally destroy your solution, whereas a good mesh will lead to a accurate, robust, convergent solution. So challenges in CFD is to obtain higher order, accurate, non-oscillatory. That means your solution should not oscillate. It should be stable, and it should be converged solutions and capturing contact surface exactly. It happens, for example, if you want to obtain the skin friction coefficient, we solve Navier-Stokes equations, and the skin friction becomes very, very important, because for drag and other studies, this forms very important aspect. So contact surface exactly and free from numerical shock instabilities at the same time. So all these aspects, they are the challenges in CFD. You have to develop algorithm in such a way that they satisfy all these conditions. So accurate capturing of shocks and boundary layer in high-speed flows test the ability and robustness of both flow solvers and mesh generators. So flow solvers, which are nothing but the numerical methods to obtain the solutions for the PDEs, and mesh are the mesh cells, or grid points are the, a kind of either structured or unstructured distribution of points around the physical body. Yeah. So both flow solvers and mesh generators are judged for their quality based on the rate of convergence, solution accuracy, and CPU time required. The greater the rate of convergence, the better mesh quality. It means that the correct solution has been achieved faster. An inferior mesh may not capture the important phenomena like boundary layer, or it may not even capture shocks. And such grid points will also slow down the convergence, and you may not get accurate solutions. A better mesh quality provides more accurate solution. For example, one can refine the mesh at certain areas. Suppose wing body junction, there is so many things, physical phenomena taking place, fluid structure interaction and so on. You may require to refine the mesh in some areas where you want to resolve the physics of the flow more accurately. Also, this means that if a mesh is not sufficiently refined, then accuracy of the solution is more limited. So in the nutshell, I can say that both mesh and your numerical method, they are very crucial in obtaining the accurate solutions. And of course, CPU time also plays very important role. Your computer code cannot take large time to obtain a solution. So you have to come up with some methods for obtaining the faster convergence. All these challenges are tackled at the research table. They become good enough, they are taken to industry. Whatever research takes place in the institutes like IISc, IITs, regional laboratories, and so many other places, that is why institute-industry interaction should be fruitful. Your research, whatever you do, should not stop at the research table alone. It should not end up with just publishing few papers and deriving some benefits out of it. Your research should reach industry. That is how the importance of research will reach nationally important projects. Otherwise, it will end up in publishing a couple of papers in conferences and journals, nothing more than that. Yeah, now I will come to what are different industrial applications. For example, you have developed Euler equations, which are basically inviscid. What are these Euler equations? Because I don't have enough time to go through every aspect. Maybe some of the speakers earlier in the last 2 days must have spoken about governing equations in fluid dynamics and so on. See, Euler equations, basically it is a conservation of mass, momentum, and energy. okay, we obtain by satisfying these condition, conservation property. And if it is a inviscid, if you don't consider the viscous forces, then we call them as inviscid equations, and they are named after Euler. And if you consider viscous forces, they are Navier-Stokes equations, and there are so many turbulence models available. And I call a complete equation as Navier-Stokes equations with various turbulence model. Our main aim is to solve such equations which require a state-of-the-art technology, both from algorithm point of view and computational platform point of view. So I would like to list some of the projects, which some of them, definitely you may be aware, it requires a high performance computer. That is what we call it as supercomputing platforms for CFD simulations. For example, Akash, Trishul, Nag, Agni, BrahMos, there are varieties of missiles programs of DRDO, and there are ASLV, PSLV, GSLV, ISRO, and light compact aircraft of Aeronautical Development Agency, helicopter aerodynamics, so on. There is a need of the technology development and aerodynamic evaluation. And we can also talk about isotope separation through ultra high speed centrifuge, maybe in atomic research, and laser plasma interaction, and for weather prediction, fundamental research like direct numerical simulation, large area simulations, combustion, turbulence. Wherever you talk about all these physical aspects, you require good amount of knowledge in both algorithms and understanding the physical process. Further, transonic supersonic flow around missiles, prediction of aerodynamic forces and moments become very important. They form the basic, in fact. If all we call it, all the things what we call as the drag, lift, forces, moments, they're all represented by different equations which will be required to understand your physical phenomena. Because most of the governing equations, not most of all these governing equations, what we call as Euler equations or Navier-Stokes equations and so on, finally our main aim is to obtain the pressure distributions, velocity distributions, Mach number distributions, so that with that data you can estimate these aerodynamic forces and moments coefficients which in obtaining drag, lift, moments and so on. So prediction of incremental changes in aerodynamic coefficients due to control deflection and so on. And for example, I want to understand flow around launch vehicles. A satellite will be launched, and a very huge launch vehicle with the strap-on boosters, it takes it to the space. How different strap-on boosters are fired in order to identify the correct slot for this satellite. That is a challenge. It forms a very important aspect, and there are so many issues where you cannot conduct experiments. So numerical simulations will help in understanding such complex phenomena, wings, wing body, wing tail configurations, and so on. There are a large number of strap-on separation aerodynamics, and so on. Flow through the air intake ducts, they form a very important aspect of CFD. Flow through the turbo machinery, and reacting flow through nozzles. I will present before you a couple of problems what we have solved in the past, and space vehicles, hyperplanes, and so on. And even in automobile industries, flow past cars, railway engines. For example, in Japan, they call it as a Shinkansen train, Shinkansen. A very fast train, it goes very fast, when a fast moving train crosses another train, so what are the effects on the wagons? Because the flow becomes very unsteady around the wagons. So such studies are being tackled by both, experimental setup and numerical simulations. Yeah, these are the some very important. I don't have enough time. There are very large number of problems. I am concentrating more on only aerospace applications, but it is such a vast area. In fact, it has entered into all aspects of chemical engineering and nuclear engineering and maybe bioengineering. In fact, aerospace is a highly multidisciplinary area where we have, like structures, propulsion, guidance and control, and also we have aerodynamics. So it is an ideal platform to bring all experts into one, one platform where we can interact and study different aspects of fluid flow. So in our institute, there is a Department of Aerospace Engineering. This department, they are highly multidisciplinary areas. We have aerodynamic, propulsion, combustion, structures, guidance and control. We have an STC, Space Technology Cell, which is set up by Indian Space Research Organizations. We have lots and lots of collaboration with industries. And there is one more JATP, Center of Excellence for interaction with DRDO. So there are so many collaborative programs going on. So the research aspect, whatever that takes place in the institute, we take it to a final stage, that is to the industry. Yeah. It is a very simple problem. For example, what are the different forces acting on all of you, like people studying aerospace in the first year itself, they study all these things. Forces, different forces acting on the aeroplane. We call it as a lift, and this is a drag, and thrust and weight. Lift is nothing but force in a direction perpendicular to the oncoming stream. Drag is a force in a directional parallel to oncoming stream, and thrust, force generated by engine which powers the flight, and overall weight of the body acts downwards. These are the different forces continuously acting over the flying object. And there are moments also, that is rolling. Sometimes your aircraft can be rolling a slide when it wants to take turn. As I said earlier, I have shown the pictures of here a transport aircraft. So the stability is more important than maneuverability. So rolling motion, the rolling axis, and there is an rolling, yawing, and pitch. Roll, pitch, and moment. Moments, they form a very important aspect of flight aerodynamics. So all these things, we model them. We model the physical process in a mathematical formulation, and then using numerical techniques, we solve them to obtain the solutions. So lift, for example, is given by this relationship, drag and moments. Very briefly, I want to say all these things are very important. Lift, lift coefficient, drag coefficient, and moment coefficient, they become very important in aerospace design. So all these things could be very easily understood by numerical methods, simulations. And now, very briefly, I don't go through in the detail, how to obtain. In fact, I have mentioned earlier that you must have already heard by a few speakers that Euler equations, Navier-Stokes equations, and so on, they are basically governing equations of fluid dynamics. These equations, if you look at them, they are so simple. They have just derivatives. For example, du by dx, or d rho by dx, or du by dt, or d rho by dt. That is, you are discretizing du by dx. That is, you are discretizing the velocity component in x direction u with respect to space. You know, how do you discretize? I want to discretize in this way. Okay, it is called finite difference approximation. The entire task in CFD is to obtain value for your derivative, du by dx, or dou u by dou x, because most of them are partial differential equations. So, if suppose I want to estimate the derivative at the point I have a cell, my space is discretized. I have a cell at I plus 1, I have a cell at I minus 1. So, I want to put the Taylor series in this form, that is, fi plus 1 equal to fi plus fx dx and order of delta x square. And fi minus 1 is fi minus fx dx and order of delta x square. So the central difference approximation at the point I, if I want to estimate f at the point I, that is fx, is f of I minus 1 minus of f of I minus 1 over 2 delta x. So if you want to estimate the value at the point I, you require information at I plus 1 and you require information at I minus 1, okay, divided by delta x. That is the space size, or we call it as stencil size. It is called central differencing. And if you consider only the point I plus 1, it is called forward difference approximation. That is fi plus 1 minus fi over dx, and backward difference approximation is fi minus 1 over dx. So I don't want to go into the details at all. This is the fundamental for everything. You please try to understand what is a finite difference. If you understand finite difference clearly, you can solve any equations. Of course, it becomes more and more complex. There is no doubt about it. That is why we require more robust algorithms. But finally, for any algorithm, however advanced it is, however robust it is, however state of the art it is, the basic in that algorithm is to obtain the expressions for the derivatives. So I'm now talking about finite volume. In the finite volume, we form the cell. Suppose you want to estimate the value at cell J, form a cell. I will go to the next slide. You will know like this, finite volume. Suppose I want to estimate the value at xj. So I consider as xj minus half and xj plus half. So I integrate this value ux dx between j minus half and j plus half. That is, I want to estimate in this volume. Of course, in 1D and 2D, we don't call it as a volume. It is just a cell. In that cell, the volume is 3-dimensional. So just I want to mention here that there are different methods in obtaining the numerical solutions, either finite difference, or it can be finite volume, or there is a huge list: finite element method, particle method, spectral method, meshless method, and so on. There is no time to go into the details of all that, but the essence is we obtain the derivatives either by finite difference method or by finite volume method. They are so simple, you can refer to any books or introductory level in any numerical methods, talk about it. So I will not go into the further details of those things, and briefly I will talk about what is meshless method. Meshless method is nothing but you just see here an arrow phi, and there is nothing like I plus 1 and I minus 1, what we talked about. in either finite difference method or finite volume method. Here, it is totally arbitrarily distributed number of points. For example, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16. As and when a cell is generated or a grid is generated, it is numbered. So, meshless method works on a cloud of points. Any arbitrary distribution of points will do for this purpose. For example, for node 13, suppose you want to compute for node 13, the connectivity here, neighbors information is very important. Who is your neighbor? Okay, of course, it is very important in your day-to-day life also. If you have good neighbors, your life is very smooth and fine. So that way, in this arbitrarily distributed network, for example, node 13, the connectivity, who are your neighbors around 13? It consists of, for example, 2, 14, 26, and it can be 12. You draw one, a kind of connectivity, and information about fluid dynamical parameters like density, pressure, temperature of all these grid points will be required to estimate the value at 13. We form connectivity information in meshless method. Of course, it offers different challenges, but for complex bodies, generation of the structured mesh or unstructured mesh becomes very difficult. So in such cases, we go for meshless methods. In fact, we are transferring the burden of generating good quality mesh to the generation of a robust flow solver, because meshless method you need a very robust flow solver. Yeah, I will not go into the details, but this meshless method, you understand that there are issues like connectivity. So in numerical methods, we have state update formula. That means at the iteration level n+1, you need to know the value at the iteration level n, and this delta t is the time step, and this is, for example, a backward difference formula, j minus 1. Okay, to update the solution from n to n+1, you use this formula, and we call it as state update formula. And here C dt over h is nothing but your cell size, that is the space between j and j minus 1, and it is a number, and generally we want it to be less than 1 for the numerical stability. And consistency, for example, we have converted physical process into modified partial differential equations and then partial differential equations. So as your space size tends to 0 or delta t, very small time steps, that is delta t tending to 0, the time derivative and spatial derivative are replaced by consistent finite different approximations. So consistency is very important in formulating your mathematical model. You should see that your model, PDE, it is consistent with your physical process. And append property is the most advanced concept, that is based on the velocity distribution. Suppose your velocity distribution C is greater than 0, that is positive. But suppose you consider it as the x-axis, the fluid is moving in this direction, so that positive velocity C is greater than 0. I consider the points xj minus 1 and xj. To update the solution at x, j, I consider the point j minus 1. That is, your fluid already has influence of the point j minus 1. before reaching the point J. That is why we call this as domain of influence. In upwind principle, we should look into the domain of influence. If the velocity is greater than 0, we consider the point J minus 1 in obtaining the derivative. And if the velocity is negative, for example, it is in this direction, the negative direction of the x-axis, then we consider the J plus 1 point as the the point in the domain of influence. So we consider J plus 1 and J to update the solution if the velocity is negative. If the velocity is positive, we consider J minus 1 and J. That is a simple upwind property. Of course, now that methods are reached a very matured stage, so there is lots and lots of research has taken place. Various people have come up with various methods like flux difference upwinding, flux splitting. There are so many methods. I will not go into the details, but the essence is only this much. Based on certain criteria, we split the fluid dynamical parameter, for example, pressure, density, or whatever, based on the direction of the propagation of information. I can put it this way. The information, if, for example, information travels from x minus c dt to x and not the other way around. So we consider the point in the, J minus 1. The J minus 1 point is considered. We call it as upwind point. Depending on the velocity direction, the upwind point changes. That is called upwinding or upwind property. And conservation property, that is also very important. There are so many things which we should consider before development of numerical methods. Now, I would like to touch upon very briefly, over the past 30 years, we have developed several algorithms in the Indian Institute of Science jointly with various industries in the country and abroad. And these algorithms have developed in order to improve stability, consistency, accuracy, robustness, applicability, and by making them physically more and more meaningful. In this direction, nearly 30 to 35 years back, we started developing space marching code. That is 3D finite volume space marching code we developed. And it was very useful for some applications in DRDO. And then with the joint collaboration, we developed a code which was time marching. Space marching has its own limitation. Space marching code becomes not useful when it comes across subsonic pockets. It is very useful only in computing flow, in supersonic flow. In subsonic pockets, the partial differential equations become elliptic. These partial differential equations have different physical behavior. Sometimes they become elliptic, sometimes they become parabolic, sometimes they become hyperbolic. If the PDEs become elliptic, then space marching stops marching. You cannot obtain the solutions. So the time marching solutions are more widely used, and we developed a 3D finite volume time marching. That was the time around 30-35 years back. No industrial packages like ANSYS, CFD++ were available. Everything, you have to develop your own program. Even if you want to join 2 points, x1, y1 to x2, y2, you have to write a program in graphics to join those 2 points. In fact, now the young generation, what you are, want to take up this career in CFD. In fact, you are really blessed. There are so many powerful industrial packages available, and also very high-end computing platforms are available. The only thing is you have to identify some challenging problems and try to understand what you want to do before using commercial packages, because you should not use them as a black box, because no one wants to spend more time in algorithm development these days, and also it is not necessary only in research institutes, algorithm developments, as a part of PhD program they take up. But in industry, there is no need to come up with new algorithms all the time. You use existing algorithm to solve the practical problems. In fact, Dr. Kalam was director of Defense Research and Development Laboratories those days. He invited us to form a CFD task team in DRDL Hyderabad. As a result of that, this 3D time marching code was evolved, and Dr. Kalam named it as Bhima. In mythology, you come across a character Bhima who was very strong and robust, and he used to smash everything, whatever it comes in front of him. So this time marching code was very useful, and we solved several problems, both inviscid and viscous flow, and what should I say, complex physics, complex geometries. That is why he named it as Bhima, and Bhima stands for Boltzmann hypersonic Euler Equations for missile aerodynamics. In fact, he was very much thrilled by this numerical simulations, because it was not possible to conduct experiments those days. Yeah. So I will not go into this details of these theories, but we developed several algorithms based on Lagrangian particle dynamics, least square kinetic coupled method. We call it as a kinetic coupled method. Appropriate moment method, we obtain fluid dynamical equations like Navier-Stokes, Euler, and so on. So the entire method is called kinetic. So this kinetic coupled method, we call it as the least square kinetic coupled method, implicit LS-cum, and there are large number. You may wonder why we require so many algorithms. We require so many algorithms. As I said earlier, we continuously try to improve its robustness, or we try to improve its stability, or its accuracy, or its applicability, or to reduce CPU time. We want to make it more and more efficient. That is why we require large number of algorithms. For example, kinetic flux vector splitting on moving grid, and tools like PVD-MAC. PVD stands for total variation diminishing on McCormack method. All these methods were developed long back in order to solve problems which we came across to obtain the accurate solution. When we were solving the space marching, using space marching method, suddenly over a slender body, you come across a lot of oscillations in the numerical solutions. They are not physical oscillations, but they numerically obtained oscillations because of certain numerical errors. So how do you tackle them? Because you require non-oscillatory solutions. So we developed a method like total variation diminishing. These variations you diminish by appropriate methodology and so on. And this global minimum residual algorithm, GMRES, to obtain fast convergence and so on. In fact, in one sentence, I would like to say, that is, we started the CFD activities, we lived with this, and it is something like giving birth to a child, and giving it a good education, a good culture, and making him a good citizen in the country. It is something like that. CFD in IISc, it started 40 years back, and now it is in a very, very, very matured stage. We can apply CFD techniques to varieties of problems, and people who are trained in IISc, they are now heading all over the country in different places, and this field is contributing in national projects. Yeah, I don't want to go through into the details. This is the growth of computing power in IISc, for example. If you consider in 1975, there was nothing. 1980, this was the first computer, DEC 1090. Okay, you will be surprised. It was such a small computer. The entire computer had not even 1 MB of memory. In fact, these days your mobiles will have 120 GB, 128 GB, 256 GB, and so on. So those were the days we started doing CFD around 1980s, 82, 83, 84, and so on. Absolutely no computing power is available, and with existing power, we could understand some of the phenomena which helped us in developing the technology when faster and faster computers became available. Around 2000, in IISc CFD Center, it obtained PACE 128, that is Processor for Aerodynamic Computation and Evaluation. It is a parallel computing platform generated by DRDO. There is a center or laboratory called Anurag, Advanced Numerical Research and Analysis Group in Hyderabad. They are responsible for developing such parallel computing platform. And jointly with IISc, we installed in CFD Center, IISc, and in fact, you will be surprised, this entire huge machine had just 128 GB. That was 8 GB on each node, and it was 16 node machine. So we could have just 128 GB. But those days, around 2002 and all, 20 years back, we could solve some very complex problems. And nowadays, you will be surprised. For example, IISc, around 2015, it acquired a computer called Sahasra T, a general purpose supercomputing platform. It can do quadrillion, 10 to the power of 15 calculations cores are in clusters. Okay, and accurate communication between different clusters and cores. And you will be surprised, within 3 days, 80% of computational resources were saturated. So what I want to impress upon, more and more higher computing platforms, they become available. At the same time, you are so desirous and so much complex problems are evolving. So you want to understand the physical phenomena in a more clear sense, or you want to resolve finer aspects associated with complex phenomena. So such high-end computing platforms have become very useful. Now in the country, you have Pratyush and Mihir. They are the only 2 computers faster than Sahasra T in the country. But these 2 computers and all these high-end computing platforms, they come with the end-user certification. You cannot use them for certain applications in defense sector, nuclear sector, space sectors, and so on. You can use them for weather changes, studies, climatic changes in Mosambhan, Delhi. Yeah. Before I close this topic, I would like to say verification, validation, and certification become very important. What are these things? Verification is numerical. Okay. The validation is physical, and certification is done with a design and operability which works on real-time configurations. And validations are done with benchmark experiments. So when a CFD code is generated, using a new algorithm, a verification stage is very important. Nowadays you use industrial package, and already industrial package has gone through all this exercise. So you don't have to do it, but as a trainee, as a student, I always impress upon students to validate them, because you understand the procedure of validating. What is the verification and validation? So verification is grid refinement. How do you know that particular size grid is optimum? You should not use more number of cells. At the same time, you should not use, inadequate number of cells. You have to obtain the accurate solution. So that can be obtained by only grid refinement study. You keep on refining the grid, try to make it finer and finer, and try to obtain the solution, and try to find out, whether you get a residue fall and a consistent converged solution. That is called grid refinement. And also you should watch whether your residue falls consistently. And intercode comparison. Two different codes developed on two different algorithms, you can always compare and find out whether they give the same solution. So that also becomes very important. And validation forms comparing numerical simulations with benchmark experiments. In our country or even abroad, most of the time I see people using verification, validation interchangeably. They do verification and they say that they have validated. If you compare with another numerical simulations, suppose you have used ANSYS and comparing with MSc software, or MSc software with CFD++, or some other code which you have developed yourself, all those things form verification. Validation forms only when, or validation exercise completes only when you compare numerical simulations with carefully conducted benchmark experiments. Okay, or at least, you may refer to some experiments which are openly available in literature. You can compare your numerical simulations data with benchmark experiments. Unless you do it, your numerical simulations are not validated. Certification is the last stage where you have to run your program for the realistic configuration, either for fighter aircraft or missile or transport aircraft or whatever. You must come up with error bands. One thing you remember, numerical simulations are not exact solutions. They are always associated with errors. Numerical simulations, when you say, I have obtained drag, some value, for example, 0.8, 0.9 or 2.2 or whatever, some numerical number, you should be always associated with error band. What is the percentage of error in predicting or in simulating or in giving this data? That drag is predicted by using numerical simulations with 5% error, 10% error, 15% error, and so on. Any numerical simulations not associated with error bands, okay, some of the journals, they don't even accept such work. Always numerical simulations should be associated with error bands. And then you should come up with the operating envelope. What is your code? Does it work between Mach number 2 to 4 or subsonic for Mach number maybe 0.6 to 0.2 or maybe 0.6 to 2.1? Whether it is code, what is the operating envelope where your code is useful? Because a general purpose code is not possible because the physics is different. Subsonic physics is different. Supersonic physics is different. Hypersonic physics is different. The approximate solutions, the partial differential equations representing physical process become different. Turbulence models are different. So, what is the operating envelope over which your CFD code can be used? And the next one is acceptable CPU time. How much time it takes? It cannot take days together, months together. So, a certification, when you say that your CFD code has gone through certification, it should become industry package code. Then you imagine this ANSYS, CFD++ or MSc, whatever industrial packages commercially they're available, they would have gone through various stages of verification, validation, and certification. Only then such codes are called as industry standard design code. Unless it is done, you cannot use it for design studies. We did it long back for a missile type of configuration using wind tunnel data. I don't want to go through in detail. Those days computers were, did not have much power. We used to talk about only 100,000, 300,000, 500,000, maybe 100,000, 1 million points, like that. Nowadays, people talk about, huge mesh points. So somebody can take up and do, in-house developed codes. We validated and verified BHIMA KFES and BHIMA PVO, two different algorithms developed for the same application to solve fluid flow around generic wing body tail configuration. And wind tunnel, NAL wind tunnel data we use. And those days, DEC alpha, ultra spark, some parallel computers we use to undertake this huge analysis, verification, validation, and certification studies. We could come up with error bands and see here, this is called Reddy-Reckner plot. Our estimation, for example, this is estimation of drag coefficient, without skin friction, because we have run only implicit code. We did not have enough resources to run viscous code those days. So it is only a kind of presentation. You try to understand that I have plotted Mach number versus angle of attack. So, these are the error bands: 5% error, 10% error, 15% error. So for Mach number 1.52 to roughly around 2 or less than 1.8 or something, the error associated with our predictions was very less. And as you go, more and more in Mach number scale, higher Mach numbers, the error was more. What I mean to say here, what I want to send a message is, always your prediction should be associated with error bands. If you don't do that, your numerical simulations have no meaning. And I will just briefly, one or two problems I will present before you before I close my talk. One was, Akash, air intake, and in practical situation, used to suck air from the atmosphere, and then before going to the combustion chamber, lots of oscillation, very violent oscillations used to build up. This is the configuration, this is the wall, and this is the spike. We call it as the air intake. And here you will have the combustion chamber. So for supersonic flow, they found huge, massive oscillations, or violent oscillations, I can say. And this problem was posed to us to, first of all, why oscillations take place, and what are the implications of these, and how to suppress them. And we did intensive study, by generating mesh, block structure, block 1, block 2, and mesh. And then we could capture, the oscillations. These were the oscillations at different locations along the air intake. And we compared these oscillations with flight data, because experimentally it was not possible. We did not have any wind tunnel data, but we had flight data. This flight data and our numerical simulations matched very well. That is how we could establish confidence in our numerical simulations. And these are different, pressure plots and isopressure in air intake. And another application was mobile launcher. We require mobile launcher for missile launching, because everywhere we cannot build mobile stations. So these, mobile launchers help in launching different type of missile vehicles. So the CFD studies of heat transfer, when this missile flies, generates heat around this shield, and this launcher, the material, should be able to take that heat. So we did a lot of analysis. we could come up with Mach number distribution, velocity distribution, and temperature around this launching platform, and they were all very useful for the design studies. So another important problem was multiple nozzle driven laser cavity and diffuser. This is also of importance to defense. Laser cavity, they wanted to generate a very huge, powerful laser. So they wanted to understand the fluid phenomena, aerodynamically controlled laser cavity for the generation of high powered laser beams. In this situation, it was a kind of active lasing medium where rapid and deep cooling of a mixture of gases, carbon dioxide, N2 and H2O from a combustion chamber is achieved by allowing the gases to expand in a set of convergent divergent nozzles and allowing the supersonic jet to drive the cavity. It is the formation of supersonic cavity. They wanted to optimize the diffuser lengths, because here optimization plays very important role in the design studies so that they can reduce lot of cost and also increase the efficiency. So the bank of nozzles, cavity, diffuser, they all form the unit in this particular experiment. Something like this. This was the inlet. The gas comes from the combustion chamber. The project was aimed at simulating flow through the multiple nozzle-driven laser cavity, diffuser and thrust control device, and to validate CFD predictions. We could generate the appropriate flow. We could numerically simulate, and also we could study the flow in this convergent and divergent nozzles. This is the nozzle bank, and the cavity forms here, and these are the diffusers. And the moment the flow reaches here, it is called pressure recovery. It will be very high pressure, to the comparatively low atmospheric pressure it should come. We call it as pressure recovery. We could achieve it very successfully. There are different plots. Here you can see, it was from the pressure recovery took place very efficiently, and from you can see from almost 30 atmosphere to 1 atmosphere. And also we did a lot of work on transport aircraft, both numerical simulations and experimental in wind tunnel subsonic flow in IISc. We could validate, you see here, experimental data and numerical simulations. They match very well, and large number of other studies were done. And some non-aerospace applications like Calendria flow for nuclear reactor, numerical investigations were carried out in order to optimize the inlet and outlet parameters so that safe working, you have to pump in some fluid in order to keep this temperature moderately. So such very complex physics problems were numerically tackled, and we could give some important data to the industry. So we have done some work in biofluids also. I don't have much time to go through. We could simulate the blood flow through the artery, and this study is not extended further. We want to take it up further, but we have started this activity, biofluid dynamics, using the numerical simulations. They become very useful in designing apparatus experiments while conducting operations, so that blood loss during the operation will be minimum. Yeah, this is a very important slide. We have several promotional activities, both institutional and multi-institutional involvement, and institute industry interaction, and symposium, conferences, invited talks, and so on. This is the conference I don't have for 20 and 21 because Corona, we could not do it last year. We hope in 20 we do, 21 we will do it. Every year in the month of August, it takes place in Bangalore. Okay, I'm the co-chair of this particular event, and we invite several papers, contributory papers, invited talks, and there are student section, so that students also can come. We pay them, travel expenses, and we provide them, accommodation. The whole idea is to promote CFD activities in the country. Younger generation should be should find some kind of career in this field. So from that point of view, we conduct this annual event. It is called Annual CFD Symposium. It is conducted by CFD Division of Aeronautical Society of India in the country. It has become very popular, and in fact, this year it is a silver jubilee. Yeah, we started around 1998 or something. We have already completed more than 22, 23. 97 it started, I think. We are approaching the silver jubilee soon. This is one of the very interesting and very important physical activities. And you see here, we circulate, and also you can find it through website of Aeronautical Society of India. Apart from this, we conduct spices, that is indigenous CFD codes are subjected to CFD simulations. We invite foreign participations. We identify the typical model. We conduct experiments in laboratories like CSIR, NAL, IIT Kanpur, and so on. And we invite many people to participate in this activity to conduct successful verification and validation studies. I finally dedicate my talk to my wife, Vasanta Prakash, who is no more, and she was a very constant source of energy, enthusiasm, encouragement to me. I would like to thank all of you for patiently listening to me, and I would like to invite participants to Indian Institute of Science in Bangalore. If you come here, you can visit many aerospace laboratories. Thank you so much. Thanks a lot. I thank once again the organizers for giving me this opportunity. Thank you.
Thank you very much, sir, for such a wonderfully structured and eye-catchy presentation. It was amazing, sir. Is there any participant having any question? Participants, they can ask the question now. Yes, anyone having any queries or question?
If if there are no questions, two things can happen. One thing is you must have understood everything what I have said, or or maybe you are yet to. Anyway, in any case, I have given my email ID to Professor Thakkar.
Yes,
you can always communicate with me on WhatsApp, mobile, any mode of communication. I always like to support young generation, younger students, to come up and take up this CFD as the some career. I would like to share with them anything they would like.
Sure, sir.
Good afternoon, sir.
Thank you. Thank you so much.
There is one participant. We want to say.
Yeah.
Sir, good afternoon, sir.
Yeah.
Sir, I am Nirmal Kumar, sir. Sir, I have, if I want to contact you in regarding CFD, you help me, sir. Because
sure. You send an email. Professor Thakkar has my email. It is a, maybe I will show you the first slide.
No, sir, you said that you can contact with me in WhatsApp or any.
Yeah. You can contact me in any mode. No problem. I will tell you.
Sir, I have one question, sir, regarding.
Yeah.
Sir, in Meshless software, sir, that in Meshless software, because I read somewhere else that the grid is not getting accurate solution in Meshless software. It is a
3D.
grid generation
Ah,
is not accurate as in other which is a meshing software. So the meshless software is not accepting any industry or any research field.
in fact, my answer to your question will be like this. In fact, we have solved several 3D problems using meshless algorithm, like wing body junction and launch vehicle with the strap-on boosters and payload flying at a very high Mach number and so on. It depends upon your algorithm, because meshless method, in the sense, as I said in my talk, your algorithm should be very robust. I have no idea, because as far as my knowledge goes, industrial packages, whatever is available in the market, they haven't incorporated this methodology into their code. All these methods are available in only research institutes. And if you visit Bangalore, IISc and NAL and DRDL Hyderabad, National Aerospace Laboratory in Bangalore and Defense Research Development Laboratory in Hyderabad and IISc in Bangalore, a large number of 3D applications have been solved successfully. Problems have been solved. Of course, there are many issues. Nothing like, as I said, numerical simulations are always approximate. It is evolving. Definitely, meshless methods are new and still there in the evolving stage.
Sir, I would like to say that I will start my thesis, sir, from May or June. So I need help, sir, from you. So I can visit anytime, means
Yes.
in IISc Bangalore.
Yeah. Where are you studying?
Sir, actually, I am pursuing my master degree, sir, in CFD, MTech, in Aerospace department only.
Of which university? UPS?
Yes, sir. Yes, sir. Sir,
There.
sir, I want to say, sir, that my thesis topic, sir. So regarding this thing only, I want to discuss, sir, with you. So because I need some guide and help, sir.
Sure. Yeah, I think I am constantly in touch with your university. I was also in your board of council some time back. There is one Professor Joshi, and I don't remember names, but there
Yes,
are
sir.
many people whom I know.
Yes, sir. He is a HOD of
Yes.
aerospace
Yeah.
engineer. Yes,
And
sir.
Govan was there, and he left, I think.
Yes, sir.
Yeah, you are welcome.
Yes, sir. I will come, sir. There, sir. I will visit
No.
to you,
Yeah.
sir.
No problem.
Yes, sir. Yes.
Yeah,
Thank you. Sir, you can share your WhatsApp group, sir. You can add me.
No, I don't have group as such. My mobile number is, you can note down. I have not written in this slide, but you have my email in this slide. You see the slide now?
Yes, sir. Yes, sir. Yes, sir.
Yeah,
I will
psk@iisc.ac.in.
Yes, sir.
Okay,
So, sir,
you said,
sir, for 1 year, my thesis will be there, sir. So I need help, sir, from you.
sure.
Okay, sir.
Yeah,
Thank you, sir.
Yeah,
Thank you.
Thank you. Yeah.
Thank you very much, sir,
Thank you, Chaturji.
first for accepting our invitation and delivering such a wonderful presentation. It was
Thank
all
you.
the way pretty engaging, sir. Your work is really amazing in this area. So thank you very much.
Thank you so much. Thank you so much. And once again, my apology for late starting the presentation.
No issue. You are covered.
There were some problems with the network, laptop. Suddenly, as I said, things happen what you don't want.
No issue, sir.
Okay, thank you. Thank you so much.
Okay, thank you, sir.
Thanks a lot. Yeah.
And there is one announcement for participant. Today's third session is scheduled at 3:30 p.m. onwards. So kindly take a note of that. It will start from 3:30 onwards. Thank you everyone.